Okay, so in this lecture, we will be discussing about the temperature effect with the kinetic theory, reaction kinetics. So previously, we have seen that so the course outline is we will discuss about the temperature effect, the kinetic equation, then collision theory and transition state theory. So two of them, like this collision theory and transition state theory, these two are considered as the reaction kinetics or the mechanism associated with the molecular vision. And Arrhenius equation is considered as a theoretical description with the experimental finding, the effect of temperature and other parts. So let's begin with a few observations. In our daily life, what we see that because of temperature, milk turns sour. So is the formation of the curds, and then butter rancid much faster as at high temperature. Then we saw that eggs hard burn is more quickly at the sea level. That's because in normal temperature, and cold-blooded animals, they, especially the reptiles, they tend to be more lethargic in during cold season. Um, and we have seen that they go for hibernation. We will see that how these things are connected with kinetics. So the effect of temperature in biological system is heavily influenced. We see the effect of temperature. Most of the biological system are heavily influenced by the temperature, and our previous knowledge about reaction kinetics, we know if there is a chemical reaction that is suppose there are two reactants X and Y and they are forming the products. In this case, we can write down the rate equation in terms of we have seen this for our previous knowledge, and the rate of a reaction, like in this case, this reaction is depends on two factors. One is the concentration of the material itself or the reactant. Another is rate constant. So what does it mean? If I want to tune the rate of a reaction, we can do two things. One is we can tune the concentration, we can change the concentration, and that's why control the rate. Also, we can change the rate constant. Now, rate constant is a method. Rate constant cannot be tuned from outside. So this is the integral property of the reactant itself, and there are other parameters that can change this rate constant. As we say, that this is a rate constant. So, but truly speaking, this is not a constant. This parameter is influenced by several factors, and what are those factors will be discussed. That is our main point of discussion of this lecture. So, Swedish scientist Svante Arrhenius, he proposed a relationship between the temperature and the rate constant, and that relation is known as Arrhenius equation. But before Arrhenius, the observation with respect to some chemical reactions, it has been established that the rate increases twice per each 10 degrees centigrade increase of temperature. This was the general observation. Now, so if we go prehistory of Arrhenius, so this William Lee's experiment, he proposed some relation of temperature and he first William first proposed the relation of temperature and rate constant, but at that time it was not well behaved with the experimental finding. Later, Barthelot he proposed another relation that is very much similar to our present relationship. Some exponential condition with exponential function or with temperature, but it was not that much intense. Later, some experiment was supported with this equation, but later Hood did a lot of experiments with this. So Hood proposed a different relationship with temperature and rate constant, and where A in this equation A and B are two different constant that those are experimentally finding experimental observed parameters. Now later this Van Top actually did a major contribution in this field. So he, in one of his pioneer work, he actually connects these thermodynamic parameters with temperature. Now this Kc in this equation is the equilibrium constant, and we can write it down that the Kc is basically K1 divided by K2. So what is K1 and what is K2? K2 is the forward rate constant and K2 is the backward rate constant. So that means a chemical dynamics or a chemical reaction is connected with the thermodynamic parameters through some specific definition of another parameter. In this case, that is the equilibrium constant. We'll see later a little bit more. But Van Top didn't stop over here. He actually gave some estimation the exponential relation with the rate constant, and he also proposed that the free energy is connected with this can be connected to the chemical reactions. Moreover, he also thought that the pre-exponential factor like this, the constant over here, also temperature dependent. We can write it down if we rearrange this equation like A e to the power minus B into e to the power minus dt square divided by RT. Into the power minus b divided by RT into e to the power minus dt square divided by RT. So in this form, this pre-exponential factor over here, we can write it down as a prime, where a prime is equals to a into e to the power minus b divided by RT. So in this case, we can say that this pre-exponential factor is also depends on the temperature. So it was an extension of his previous proposal, and this equation was later supported by various experiments. After Van Top, Arrhenius did more experiments on reaction kinetics, and he took the very simplified version of Van Top equation, which is represented as in this form, which is nowadays known as Arrhenius equation. In this equation, there are several factors or parameters. This is the rate constant that we have already seen we have already seen in the previous reactions. This A is called pre-exponential factor, and this EA is called activation energy, and R and D are gas constant and temperature. So this in this equation, what we can see that um, the relation of temperature and kinetic the relation of temperature and rate constant is not linear. It's some exponential function of this. And if we try to find that what are the other possibilities experimentally, the connection between rate constant and temperature, there we can find four different curves. This is like temperature on increase of temperature, rate constant is increasing, or the rate of reaction increasing. This is very normal. Most of the reactions shows this type of behavior. In this case, initially the rate increases and then saturates over there and then decrease. So this is another type of observation. And in this case, another case, with increase in temperature, rate decreases. So these two are the actual reactions known is very small, very little. So one of the reaction for this kind of behavior is found in NO2, NO plus O2 NO formation. So this type of reaction is considered, if we write down the rate equation for this, it will be like a rate equals to NO square O2. But if the reaction if the with some constant, but if we write it down this rate expression, the equation should not be follow this type of curve. So rather, the reaction mechanism proposed shows that this reaction is not a single step reaction; it's a multi-step reaction, and one of the steps, one of the multi-step process is absorbing. It's not release heat, but it is some absorbing heat. So the reaction rate decreases over there, and that's why the rate of the reaction after some saturation it decreases. And in the fourth one, here initially the rate increases and then suddenly it bursts up. So these type of reactions are found for a polymerization reaction, polymerization chain reaction. Now, another representation of Arrhenius equation is like the logarithmic inverse plot. So what does it mean? It means that if we consider this Arrhenius equation of this form, if we take logarithm in both sides, what we can say that rate log of k is equals to log a minus A by RT. Now, we can see from this relation that R into 1 by T. If I write down like this, then if we plot logarithm of rate constant versus 1 by T, is a kind of a linear equation. Now, if we go draw the picture, then it is the equation, and the slope of this equation gives us the information about activation energy, and also from the intersection we can get the information about the free exponential factor. So we can also calculate the activation amount of the value of activation energy from this theoretical expression. So what does it mean? It means the change in temperature, change in reaction length, logarithmic change of reaction rate per unit change in temperature is connected with activation energy. And so what does it mean? It also means that for low activation energy, a fast reaction, and for high activation energy, it's a slower. The rate is slower of a reaction. Now, once we have the data for a reaction rate and temperature, we can draw this type of curve and we can calculate the slope, and from this slope we can get the information about the activation energy. So if we think about a problem for this, so this type of data are collected from one set of experiments. So how to deal with this? We have to calculate 1 by t from this t data, and then we need to also calculate the logarithmic of k. Once we have these two, let's draw the curve for logarithmic k and 1 by t, and we can see that the data points will not be in a linear fashion. We can now fit with a nice straight line, and from this point we can calculate this activation energy. So let's take it as our homework and let's solve this. Now, after this, what is the connection between the thermodynamic parameter and the reaction rate? So, reaction chemical kinetics is basically dealing with the rate of reaction, that is totally time dependent part, and thermodynamic is connected with the change of energy or the heat exchange process. So, they are very different, but what is the correlation between these two? Van 't Hoff, if you recall that the previous expression, Van 't Hoff gave one idea that the logarithmic value of rate equilibrium constant is connected with this free energy, right? So let's consider a reaction where A, B and C is a reactant and it is forming this product, and in a due course of time it gives another reaction that this reactant itself is giving the same product. So that means, what does it mean? It means that this is a reversible reaction, and this reaction is K1, K2 and A, DC. So this equation, this reaction is nothing but a reversible reaction, where the K1 is forward rate constant and K2 is backward rate constant. Now for each and individual reaction, we can write down the rate equation, Arrhenius equation for each part. Now from these we can calculate the K1 divided by K2 is equals to e to the power minus E1 minus E2 divided by RT. Once we have this, we can take, what is this? The left hand side is nothing but equilibrium constant Kc, and right hand side is e to the power minus E1 minus E2 divided by RT. Now, as both the reactions are happening at the same temperature, we cannot change the temperature, but rather what is happening? The reversible reaction path, the barrier crossing, the major change is the rate and temperature is constant. So that means we can explain the change, the major change will be inside the activation energy, not in the other factors. So from this equation, what we can write? We can take the logarithmic part of these both sides is C minus delta E divided by R. Now what is delta E? Delta E is E1 minus E2. What Arrhenius did for this type of relation, he used the Van 't Hoff equation just like this method, and he told that this delta E is connected with del H by RT in the Van 't Hoff equation. So what we see that delta H is nothing but E1 minus E2, that is the difference in energy. Now, what does it mean? It means that the reactant and the product, they are basically facing two different activation energy, and the difference in their activation energy is connected with the heat of the free energy of the process. Now, from this equation, there are three possibilities. One is this free energy could be greater than 0, that means E1 greater than E2. What does it mean? E1 greater than E2. So, in this case, the barrier height for this, the reactant and the product is much higher than this. So, in this case, this much amount of energy will be absorbed by the product. So that's why this is in the other case, delta H less than 0. In this case is E1 less than E2. So E1 less than E2, what does it mean? This is exothermic. And another possibility is delta H equals to 0. That means the activation energy in both sides are same. So in this case, the process will be mostly driven by entropy factor. So one example for delta H0 is the melting of ice. So in this case, the amount of energy is more or less same before and after, but the amount of entropy increases when ice melts over there. Now, uh, uh, now we will discuss about the activation and the catalyst effect of catalyst. So we know that catalyst can change a rate of a reaction. How? So mainly the catalyst changes the activation energy path or activation energy barrier. So suppose if this is my main reaction or main kinetics, the positive catalyst, that means whichever they increase the rate of a reaction, those are called positive catalysts. They reduce the activation energy barrier. What is activation barrier? In this case, this amount, and this activation barrier will be generated by positive catalyst. In case of positive catalyst, they increase the rate of a reaction. Where about negative catalyst, they decrease the rate of a reaction. So that means effectively they increase the activation barrier. So the new path will be generated for negative catalyst to be much higher than the main reaction. So so far, let's finish over here. Then in the next section, we will see how the pre-exponential factor or the rate of a reaction is connected with the other theories in chemical dynamics.